wind belts by using an animation. So these are the things we have already looked at, the winds, the surface pressures, and so on, the three-celled structure. So let's start by looking at the idealized circulation again. Idealized because we have again ignored the asymmetry of the continental configurations and just assuming as if it's an aquaplanet with maximum heating happening on the equator. We will see that this is not really the case when you add the asymmetries because of the continents and the ocean energy movement and so on. So what is the idealized Hadley cell look like? So essentially you have the heating, maximum heating on the equator with warm temperatures, low pressure, and air is rising and hitting the tropopause and then going towards the poles and sinking and coming back, right? So divergence at the top, convergence at the surface into the rising air. Well, the other additional complication that has been added here that's not so obvious immediately is something that I didn't mention before when I mentioned tropopause. We looked at a generic profile and said tropopause is between the stratosphere and the troposphere, but actually it turns out that on Earth, as you go away from the tropics, air is getting colder and the atmosphere is getting denser, so it's fitting into a smaller volume. So the tropopause actually drops. In the tropics, it's about 10 to 12 kilometers high from the surface, and as you go poleward, it's going to sink to about 8 kilometers. So there is a continuous drop in the tropopause height from the surface, and that's what this blue arrows are showing. As they go poleward, they are getting closer to the surface. As you can see, the cell is like an almond shape rather than a circular shape, right? So nonetheless, the concept is clear. Now let's add the tropical and mid-latitude components of the winds to this. So you have the northeasterly trades and the southeasterly trades converging into this low pressure. Looks a little bit asymmetric here, even though I said it should be idealized and symmetric. Nonetheless, ITCZ, which I mentioned, the ITCZ is the Intertropical Convergence Zone. It's called intertropical basically because it is not on the equator, it's slightly into the northern hemisphere, as we will see later on, because of this asymmetry in the ocean heat content and land distribution. But nonetheless, the southeasterly trades and the northeasterly trades converge. Air is rising, expanding, and a lot of rain is happening. So there is a very strongly defined, very well defined rain band through the entire tropics that is called the Intertropical Convergence Zone. And the air that sinks in the Hadley cell in the subtropical highs, shown as H with this yellowish color, at 30-degree latitude is the subtropical high, and you have prevailing westerlies to the north of it. Even though those winds are actually southwesterlies, they are mostly strongly westerlies, so they are called westerlies. Similarly, you have the same kind of flow in the southern hemisphere, where because of the ocean configuration and the land configuration, you can already see that the subtropical high looks very different. Okay, when we look at the seasonal cycle later on, we will see that as the sun moves north and south, the maximum heating also moves north and south. So the ITCZ also moves north and south, and the sinking region also moves north and south. So the high pressure centers shrink and expand with the season, and along with that, the subpolar low also shrinks and expands with that. And that's very strongly seasonally dependent. Let's add high latitude component to that. You have the polar high pressure that's pushing air out towards lower latitudes and lower pressure. Coriolis is going to act on it, and it's going to make them easterlies. And from the subtropical high, the westerlies that are going north are going to meet the easterlies in this subpolar storm track, as it is called, the low pressure band, similar to the tropical low pressure band. That's not called any kind of convergence zone. Typically it's just called a storm track, and we'll look at it a little bit more later on. So looking complicated, but essentially if you remember all the fundamentals, it's still the same. So what we will do is add a little bit of the upper air circulation to this. Why? Because as I said, as the air is moving towards the poles in the Hadley cell, for example, Coriolis is going to act on that poleward moving air as well. In the northern hemisphere, it's going to be deflected to the right. In the southern hemisphere, it's going to be deflected to the left. So essentially you end up with this strong upper level jet. So there is one called the Subtropical Jet Stream, which we don't talk much about except during the monsoon season, and the more popular one, more well-known one called the Polar front, or the Polar Jet Stream, which is really strong, much stronger than the Subtropical Jet Stream, and that is typically what is used by flights to fly across the oceans or fly across the continents in Europe and US and so on. So many flights, as you know, when you go from east to west, they take somewhat longer than when you fly west to east, because the flights tend to use the jet stream as tailwinds to move faster when they're going from west to east, whereas when they go from east to west, they have to go through these headwinds and it takes longer. So this is kind of the story of the winds, the surface pressures, the intertropical convergence zone, and so on. So we have added several concepts which you should pay attention to and make sure you understand, because these concepts will keep coming back again and again all the way into global warming, because with global warming we will just want to see how the Hadley cell is changing, how the jet stream is changing, and so on. So everything comes back to how the climate and the basic circulation, or what we would call natural variability, changes with increased greenhouse gas effects.